Okay, tonight's session is going to be focused on radicals. So we're going to be simplifying them, dealing with negative exponents, multiplying, adding, and subtracting them. So let me go ahead and pull up the first practice problem here after I share screen. Okay, so now that I have my setup, let's go ahead and start talking about the first question. This one is, there's not a lot of work to show. It's just the very basics of how we can use the radical form and exponential with fractional exponents, how we can change them back and forth, which is going to help us a lot when we apply that to simplifying and reducing radicals later on. So you may be familiar with the term power over root. Sometimes professors might call them exponent over index. They both mean the same thing. So whichever one you want to use is fine. I personally like to use the power over root. They mean the same thing, but I just like those words better for some reason. So what that means is if we're given something like the fifth root of x to the third, well, in order to rewrite this, I just keep the same base of x, so that doesn't change. But instead of having a radical, I'm going to change it to where I take the power for the numerator, which is going to be 3, and I divide that by the type of root that I have, which is 5. And that's it for converting. This could go either way. So if we were just given the x to the 3/5, we'd be able to change it back as a radical. So it goes either way, and it's pretty helpful when you're simplifying or reducing, and we'll see that more as we go through the other problems. But yeah, this one didn't really require a lot of work to show. It's pretty much just that one step. So when I put up the practice, I'll give you just a little bit of time. This one should be pretty quick. Okay, with that one being a one-step question, do you need any more time? Okay, so again, like the previous, we want to rewrite this into power over root for our fractional exponent. So now, of course, if you don't see a power, then we can just assume it's a 1. And so when we keep that base and then we do power over root, our power is going to be a 1, and the root is a cube root, so it's just a to the 1/3, and that's it. So let's move on to the next question. Now, this one is wanting us to simplify, so we don't necessarily, that trick we did before is going to be useful. I mean, technically, I guess this is something you do in the calculator, but we really want to get an understanding of what's going on and how these are breaking down. So, of course, we're going to do it by hand. So this is where we're going to take it from the exponential form and put it into radical form so that we could break it down piece by piece. So the base of 32 stays the same. And if we have our power in the numerator and root on the bottom, that means that our power is to the 4th, and our root is a 5th root. Now, it shouldn't matter where you place them. However, just keep in mind that taking the root of something is going to make that number smaller. So it would be more beneficial to make the number small by taking the root first, if possible, and then raising it to the power. Because raising it to a power will make it big. And it probably wouldn't be in our best interest to do 32 to the 4th. So we could just break it down by doing the 5th root. So we need something that multiplies to itself 5 times to give you 32. It's going to be a 2. So that whole inside, the 5th root of 32, just reduced down to a 2. Now we can deal with that power, and 2 to the 4th is going to give us 16. So did that make sense before I put up the practice version? Okay. So here's the practice. And again, these are pretty quick, so I'll give you about a minute. But I mean, you can let me know if you need more time or not. Are we ready to go over this one? Okay. So we have 64 to the 2/3. So we know base doesn't change, still a 64. The powers to the 2nd power, and that 3 on the denominator means we have the cube root. So if we take the cube root first of 64, we're going to end up with a number times itself 3 times to give you 64. It's going to end up being a 4. We still have to raise it to the 2nd power, so we get a 16. So now the next set, pretty similar, but now we're going to start mixing in negatives in the exponents. So this one kind of goes back to some old properties that we may have seen before. That one in particular for this type is if we have a negative exponent and we want to make it positive, we just flip it and it becomes positive. So that's something we have to keep in mind when simplifying this down. So looking at the first one, and I'll use blue so I don't get mixed up. Before we can change this to the power and the root, we'd want to first get rid of that negative in the powers place. So based off our rule here, that means that 4 is going to have to flip down into the denominator. Which would create a positive power. So now we should be able to do that conversion that we did before. So we'll have the 4 is our base. If we have 3 over 2, that's power over root. So the 3rd root and a regular square root. Now it's up to you, you don't have to. Typically in books and homework, they're not going to show you that 2 in front, but if you'd like to fill it in just to see where that 2 went, you can. So the square root of 4 is 2, then we still have to cube that, so 2 to the 3rd is going to be 1/8. So that's all we have to do for the first one. We've reduced it and we've satisfied the requirements. It's simplified and there are no more exponents in our answer. So that's good. Now we can look at the other one, 1 over 16, the negative 5/4. Now there is a difference between the first one and the second one. We're not going to notice too much of a difference because this one has a numerator of 1, and pretty much anything we do to it, raising it to a power or taking some kind of root of 1, it's not going to change. It's going to remain a 1. But I'm still going to kind of go through the steps just so that if you come across something that does not have a 1 in the numerator, you can still see what the process would be. Now, in the first one we did, the one in blue, we only had to deal with the 4 because there were no parentheses and no fraction. It was just that negative 3/2 attached to the 4, so that was it. This one, we have a fraction in parentheses, and the negative 5/4 is affecting both the 1 up top and the 16 on the bottom. So first things first, we do have to take care of that negative, so it's going to flip. Now, typically, a 16 over 1, we would just say it's just 16 because nothing's going to happen to the 1. But again, just in case you come across something that is not a number 1, I'm just going to show you the steps with the 1 anyway. So what we can do is if everything in the parentheses is raised to the 5/4, then there's a rule that states we can split this up. So we could think of these separately and put them each in their own roots and raise to their own powers instead of all together. So now we can just focus on one at a time. So here we have 5 over 4, so that's power over root. So we have 4th root of 16 raised to the 5th power. And the same thing will happen to the 1, 4th root of 1 to the 5th. So up in that numerator, the 4th root of 16 is going to give us a 2. And that's still to the 5th power. And of course, 4th root of 1 is still 1. Then when we do 2 to the 5th, we're going to end up at 32. 1 to the 5th is still a 1. So we can just take 32. But this is just in case you have something other than a 1. It would be split up so you could work through them separately and you would have your top and bottom answers. Does that make sense before I put up the practice? Okay. So I'm going to give you another minute just to go through this one, and then you can let me know in the chat if you're ready, or if not, I'll just wait a minute and then we'll talk about it. Okay, looks like everyone's ready to go over it, so we'll get started. So for the first one, I'm just going to keep it the color scheme and make this one blue as well. So we have 8 to the negative 4/3. So with that negative exponent, again, we have to flip it before anything else. So 1 over 8 to the positive 4/3. Now that 4/3 was only attached to the 8, so the 1 will stay the same. And that bottom, we can now rewrite it into radical form. So the root is a 3, so we want the cube root of 8 raised to the 4th power. So cube root of 8 is going to be 2 to the 4th, and 2 to the 4th is 16. So we get 1 over 16 for that first one. The second one is also in parentheses, but this time the power is not negative, which is fine. That just means we don't have to flip it before we start. This one's another case where that 2/3 would go with the 1, but since it's a 1, doing the power and the root of it, it won't change, so we would still expect to get an answer of 1. Now the bottom is 125, so we would have to work that out. So instead of 125 to the 2/3, we can rewrite that power over root. So we have the cube root of 125, all of that raised to the 2nd power. So the third root of 125 is going to be 5. And then if we square that, we get 1 over 25. Okay, so I have one more step that's covering the same thing. So I'm just going to go ahead and pull that one up. So same idea here. We have that first one, 1 over 64, raised to the 2/3, negative 2/3. So we do have to flip. Now with this one, when we flip it, 64 over 1. Again, even though we have the parentheses saying that the 64 and the 1 are to the 2/3, that's not going to affect a 1. We don't have to worry about it, and actually we don't even have to put it there at all now that it's in the denominator. And then our numerator is going to be 64 to the 2/3. So now when we change that to radical form, we have a root of 3, and then all raised to the 2nd power over 1. So the cube root of 64 is 4, raised to the 2nd is going to be 16, and we don't need to really continue putting it over 1. It's understood to be there. So that would be for your first one. Now the second one, we have 25 to the negative 3/2. So no parentheses and no fraction here, so you can think of it as over 1. Since it is negative, it would have to flip. So instead of 25, we have to make it 1 over 25 to the 3/2. So now we can put that in its radical form. So 3 over 2 means we have a square root of 25. Then to the 3rd power, square root of 25 is 5. Raised to the 3rd, so 5 to the 3rd is 125. So I'm going to put up the practice. And let me know when you're ready. Okay, so for our first one, we have 1 over 32 to the 2/5. No negatives, so we can just get started. And a lot of these examples just have the 1, so we don't have to worry about it in this case. It's just going to stay as a 1. But we do need to figure out 32 to the 2/5. So we've got a 5th root of 32, all of that raised to the 2nd power. The 5th root of 32 is going to be 2. Raised to the 2nd is going to put us at a 1/4. Then for the second one, we have 9 to the negative 3/2. This one is negative, so imagine it over 1, and then we can flip. And now that makes a positive 3/2. We should be able to put it into our radical form now. So a square root of 9 to the 3rd power. Square root of 9 is just going to be 3 raised to the 3rd power. That's going to give us 1 over 27. So everyone is comfortable with that? Okay. So now we're going to use another rule that we may have seen before, the power rule. So this time we have 2 different bases, and both of them are being raised to another power. So we have x to the negative 2/3 times y to the 1/5, all raised to the 4th. So now this goes back to one of our rules of exponents that states that if we have something raised to a power and then raised to another power, then we would just multiply those powers together. So that's what we're going to do here. Since both the x and y are in the parentheses, both of them are going to need that 4 multiplied into their powers. So we're going to end up with 2/3 times 4, and then y to the 1/5 times 4. So here we have 2/3 times 4. With multiplying, we do not need the common denominator, so we can just multiply straight across. So negative 2 times 4 is negative 8 over 3. And then for the y, we just multiply across, so we get 4/5. Now, the instructions do say to write the and without using negative exponents. So since our x is still to the negative exponent, we do have to finish by flipping that one to the denominator. So that kind of uses the rule that we've been using in the previous problems as well. So the 9 and 4/5 was positive, so it can remain in the numerator. But now that x to the negative 8/3, we have to flip it so that we can get that positive exponent. Now this should satisfy their requirements. We've simplified using the power rule, and we've made sure that there's no negative exponents. Does that make sense? Okay. So here's the practice, and just let me know when you're ready. So this one has the same set of rules. They're wanting us to use the power rule to simplify this down, and then make sure we have no negative exponents for the final answer. So we've got a y to the -4th times x to the 5 halves, and that's all being raised to the 1/4. So again, we're just going to multiply it into the powers based on that rule we had. So we have y to the -4th times 1/4, and then x to the 5 halves times 1/4. And if we multiply those out, we're going to end up with y to the -1st times x to the 5/8. Now we did have one of them end up being a negative in the exponent, so this time the y to the -1 has to flip downward. So x to the 5/8 in the numerator, and then y to the 1st in the denominator. Now it's optional to show that 1. It's understood to be there if it's not shown, so you do not have to include it in your final answer if you don't want to. And that's it. Everything's positive, everything is reduced, so that's all for that. Are we okay with that before we move on to the next topic? Okay. So now we're going to start simplifying with perfect squares. So there's a couple different ways you can do this, and it's all a matter of preference. One way to do it is if you're already comfortable and familiar with the perfect squares, then you could just right away look at that 49 and know that the square root of 49 is a 7. But if you wanted a different way, you could do a factor tree, especially because not all of them are going to be perfect squares. This one is because the set just happens to be dealing with perfect squares. But later on, we will have them where they aren't perfect. So if you wanted to, you could just make a factor tree. Now, 49 pretty much just has the 2 of them, 1 and 49. It's just 7 and 7. But this right here can show you that it is a perfect square. Because when we do the factor tree, since we're doing a square root, which remember has that invisible 2, that means we need 2 in each set. So we make a pair of the same value, and that's what gets to come out. So the 49, as it gets reduced from that square root, will become a 7. And now the way we do that with variables is a little different. It has more to do with the power. Whatever your root is, you would just divide it into that power so that 2 fits into the 10 5 times, and that is a perfect amount with no remainders. So this one just happened to reduce perfectly. Another way you can think about it is if you wanted to rewrite that 49 as 7 to the 2nd, you could do that as well, because as long as your powers and your root match, it's always going to cancel, or as long as it's divisible. So 2 does go into 2 once, which is why we would only have 1 7 coming out of the radical, and then 2 goes into the 10 5 times. So either way, you're going to get the same answer, but there's just multiple ways to go about it. It's more about what you're more comfortable with doing. So I'm going to put up the practice version of this, and then just let me know when you're ready. Okay, that one was a pretty quick one, because again, they're perfect squares, so everything should be reducing perfectly. So with that 9, y to the 14. Again, if you wanted to, you can either, if you're familiar enough with it, then we would already know that 9 is a 3 when we take the square root. If not, you can show this step. 9 can be rewritten as 3 to the 2nd, and we have y to the 14th. So with that being square root, 2 goes into that 2 once, so we only get a 3 out, a single 3, and 2 goes into that 14 7 times. So that would be that answer. Okay. So now we're going to do a similar concept, but instead of the number and the variables being perfect squares, these are going to be not so perfect. So this is more where the factor tree could potentially help out with reducing these. So we have a 48 s to the 9th and then t. So up to you, you could either find the highest perfect square that will divide into 48. In this case, 48 can be rewritten into 16 times 3. With the variables, now we ended up with an odd power both times because we have s to the 9th and t to the 1st, so they're both odd. And since we have that second root, 2 would not divide into 9 perfectly. So what we can do instead is separate the bases for the s and make it the nearest even. Because if we split this up as s to the 8th times s to the 1st, we know by rules of exponent that that would still be able to combine and give you back your s to the 9th. So we haven't changed the value of anything, we're just making it look different, breaking it apart a little bit to benefit us. Now a t to the 1st, there's really no other way to break it down, it's just going to have to stay as t to the 1st. So now when we do that, we know that the 16 and the s to the 8th are the ones that we can do the square root of. The square root of 16 is just going to be 4, and 2 goes into that power of 8 4 times, so s to the 4th would be able to exit the radical. Everything else that does not get circled can't be reduced, so they would just have to stay put. So the 3, the leftover s, and the t cannot come out of the radical because they're not perfect, or they can't be rewritten to be perfect, so they have to stay. So that's one way. If you're comfortable with doing it by just splitting it up as 16 times 3, that's perfectly fine. But another way would be to just do the factor tree with 48. So you could just do 2 and 24 and just break it down, 2 and 12, 4 and 3, 2 and 2. And since we're doing a square root, we want pairs of 2 at a time. So if we've got 2 pairs of 2, that's 2 times 2 is the 4, and the remainder stays. So just in that little piece, you can see where that 4 on the outside came from and the 3 on the inside came from. So if that makes more sense to you to do factor tree, you can, especially if it maybe takes too long or you don't want to have to sit and think about all the perfect squares and divide them out, especially when the numbers get a bit larger. The factor tree is always an option as far as the numbers go. Does that make sense? Okay, so I'm going to go ahead and put up the practice and then just let me know when you're done or if you have any questions. Okay, so here we have the square root of 28, t to the 6th, and u to the 9th. So as far as the square root of 28 goes, this is where it's up to you. If you want to do the factor tree, you can. So if we were to do the factor tree, we could do this by 2 and 14, 2 and 7, and then we'd have to stop there because 7 is prime and 2 is prime. So you'd have one pair, that's 2 on the outside and the remainder on the inside. So when we factor this, that's what we should end up having. Or if you just want to think about it in terms of perfect squares, the highest perfect square that divides into 28 is 4 times 7. So that's how you break that down. T to the 6th, it's already to an even power, and we are dealing with that square root. So this one does not need to break down. It's already got that even number that we need. But the u to the 9th is odd. So again, with the highest possible, that's below 9, so 8 is going to be the next value underneath that would be divisible by 2, so we can go with that. And that would leave you with the remainder of just 1u. So we know 4 is perfect, t to the 6th can reduce because it's an even power, and u to the 8th is an even power. So we expect those three things to be able to come out of the radical, and anything not circled would remain in the radical. So square root of 4 is a 2, which we expected when we did the factor tree. T to the 6th, all we want to do is divide that 2 into the 6th power, so we'll end up with t to the 3rd. And then 2 into that 8 would give us u to the 4th. Everything else just stays underneath the radical. Does that make sense? Okay, so now, similar, but now we're changing it instead of square roots, cube roots. So the idea is the same. However, instead of looking for things that are divisible by 2 or perfect squares, we need perfect cubes or things that are divisible by 3. So we have 27, t to the 5th, and w to the 11th. Now the factor tree works for more than just the square root. So if you wanted to do factor tree with 27, you could do 3 times 9, and then 3 and 3. Now with the factor tree with the square roots, we just picked 2 matching at a time because it was a square root. Now that we're talking about a cube, we need 3 that are matching. So the amount is, you just figure that out depending on the type of root you have. So if it was a 4th or 5th root, doing the factor tree means you would need 5 of the same or 4 of the same. So since everything got circled and there are no remainders, then that means 27 is a perfect cube, which it is. It's 3 to the 3rd, so it would just be a 3. But we'll leave it for now. So we could rewrite the rest of it, or we could just do 3 to the 3rd. So with the t to the 5th, we want to find the closest thing that's divisible by 3, but still below 5. So the only way to split that up is to make this t to the 3rd times t to the 2nd, because that would still add up to 5. We do the same thing for w to the 11th, but now we want to break it up to w to the 9th, w to the 2nd, because that's going to add up to 11, but the closest thing that was divisible by 3 that's below 11 was 9. So we have to do that. So now we can only pick things that 3 can go into. So this one, the t to the third and the w to the ninth. 3 cannot divide into that 2 for both the t and the w, so they have to stay. Everything else can come out. So that's going to leave us with a 3 on the outside. 3 goes into that t to the third, into that power 3 times. So we're just left with 1 on the outside. And the 3 goes into the 9 3 times. So we get w to the third. Then we just fill in the remainder, being careful that if you start off with the cube root, make sure your answer also has that cube in there. It can be a little easy to forget sometimes when writing everything, especially if that power is a 3 and the root is a 3, that can get a little tricky, which if you feel that it could potentially get in your way, you can rearrange because multiplication order doesn't matter. So if it's something you would prefer to do, then you could change the order so that power doesn't look like it's blending in with your root. And that's as far as we can reduce, because everything in that radical, 3 can't divide into those powers, so that's as far as we can get it. Does that make sense before I put up the practice? Okay. So just let me know when you're ready. Alright, for this one, we have a fourth root this time. So we're going to have to make sure that everything can work with that fourth root. So we have 16, x to the 13, and z to the 5th. So for that 16, a 2 would be, the fourth root of 16 is 2, but if you wanted to work that out, you could. And with that factor tree, you can see that with the fourth root, we need 4 of the same, and that would happen if you did the factor tree with 16. So the fourth root of 16 is 2. So now we could rewrite that as 2 to the 4th if we wanted to. Now, since we have a 4, all our exponents have to be broken up into the highest thing that a 4 can divide into. So with 13, we can do x to the 12th and x to the 1st. And then for the z, we can do z to the 4th, z to the 1st. So the only things that we want to, or can reduce down, is going to be the 2 to the 4th, x to the 12th, z to the 4th. So the x and the z, they have to stay because 4 does not go into 1, so those cannot reduce. So we get a 2, 4 goes into 12 3 times, and 4 goes into 4 once. We still have a 4th root, so we have to put that 4 in there, and then x and z remain. And that would complete that one. Is everything making sense so far? Okay. So we may only have time for one more. And so we're finally going to get into multiplying radicals. So this is a simplified one without any variables yet. This is probably the last that we might have time for, so we'll just see. Now with multiplying radicals, we do not have to have matching radicals for these to multiply. However, it would be easier, if possible, to break down anything underneath those roots just to make the numbers a bit smaller. Technically, we could multiply straight away, but a 12 times 75 would give you a pretty large number, and then you'd have to try to break that down. So instead of dealing with that large number, we can just reduce before we follow through the multiplication. And again, you could either choose perfect squares to break these up, or the factor tree. So with 12 is the same as 4 times 3, and that's the highest perfect square that divides into that. And for 75, the 25 times 3 is, so the 25 is the highest perfect square that would divide into 75. So the 4 would get to come out as a 2, with the root 3 remaining. And now, since we already had a value out in front, just to be aware that that's also held together through multiplication, so anything that comes out of the radical would be multiplied to anything that was previously in front. So square root of 25 is going to become a 5, and the 3 does not reduce. Now this one's just coincidence that we end up with matching roots. It doesn't have to work out that way every time with multiplying. So you've got a 2 root 3 times, and then we'll just reduce this down before we start multiplying out everything else. 15 root 3. Now that our numbers are much smaller, especially in the radicals, the way we would multiply them is you always want to do outsides get multiplied, and then the insides of the roots get multiplied. So we only want to do 2 times 15 for the outside, and then you can multiply everything that's in your radicals together. So 3 times 3 is going to give us 9, and just so happens that a 9 is perfect, so it turns out this can actually reduce a little further. So now we have 30 times, and the square root of 9 is 3. So our most simplified version of this is going to be 90. Does that make sense? Okay, I think this practice might have to be the last one, because I don't know if we'll be able to squeeze a demo in another practice after this. So here's the last one, and just let me know when you're ready to go over it. Okay, so we'll get started with this one. We have 4 times root 50, and then that's multiplied by square root of 80. So definitely with these, we've got 50 and 80, those are pretty large numbers, so it'd be better for us to reduce those down first. So we'll just carry the 4. Now the biggest square root that can divide into 50 is going to be 25, and that's times 2 to make 50. And the largest that can go into 80 is going to be 16, and then times 5 to be 80. Oh wait, hold on. Yes, okay, just double checking. Alright, so for this one, the square root of 25 would reduce, so that 4 is already in front, so we'll just do the same thing. We'll just multiply them, and then the root 2 is remaining. Here, we don't have anything in front of that root, so when we reduce that 16 as a 4, it's just a 4, and then the root 5 remains. So here we can see that not every time will the roots end up giving you the same. They can, but they don't have to for these. The 4 times 5 can multiply out to 20. And then now we're ready to multiply outsides together and radicals together. So 20 times 4 is going to give us 80. And then 2 times 5 underneath the radical is 10. And that's really all we can do because there's nothing that would go into 10. There are no perfect squares that divide. And you can even double check with the factor tree. There's only 5 and 2, so there's no matching set here. So 10 is as far as we can break that down. So 80 root 10 would have to be our final answer. Does that make sense? Any other questions regarding anything that we've covered? Okay. So that's going to be it for tonight's session. We didn't get to cover the rest, but the rest will be covered on Sunday. So that one will be also from 9 to 10, and it'll cover the rest that we didn't get to, some more multiplication, and then adding and subtracting, and a little bit of conjugates and complex numbers. So that'll all be on Sunday session.